All right. All right. It's great to have you here, Eugene. Let me introduce our today's speaker for our MCQST Colloquium. So with Eugene Polzik, we have today a very special speaker who is really one of the pioneers of experimental and theoretical quantum optics and the control of light-matter interactions. Eugene received his PhD from Lenin University, where he then became actually almost immediately associate professor. And following this, he held positions, for instance, at Caltech, working with Jeff Kimball, working on spin squeeze states and non-classical light. Following that, he became professor actually at Aarhus University in Denmark, and there he received one of the prestigious Center of Excellence grants by the Danish National Research Foundation. And with that, he moved then to the Niels Bohr Institute, where actually he's sitting right now. And he became also professor at the University of Copenhagen. There he founded then his almost famous institute, the Danish Center for Quantum Optics, which became later really one of the blueprints for such centers throughout Europe. So he also was in an advising role, for instance, when ICFO was founded and so on. Then in 2012, he became director of quantum optics and atomic physics at the Niels Bohr Institute. So really following the footsteps of the name of the institute itself in parts. I mean, these are huge footsteps, of course. He is really made quantum optics and information theory really one of the key research areas, not only in Scandinavia, but really throughout Europe. And as I mentioned, his Center Quantop really laid the foundation for many of those throughout Europe. So actually, Eugene held many firsts in experimental physics. Let me just mention a couple of them. So he performed really the first atomic spectroscopy using non-classical light, and managed to perform unconditional quantum teleportation, and he also realized the first quantum memory of light and achieved cooling of nano-oscillators using light, and there are actually many more to mention. And these achievements are, of course, also reflected in various prizes he received, extending from the Gordon Moore Distinguished Scholar at Caltech, the Danish Physical Society Prize. He's fellow of the Optica Society and is member of the Royal Danish Academy of Science. As I mentioned, he received many of the big grants throughout Denmark, for instance, in Europe, including the Danish National Research Center of Excellence grants. He received not only one, I think, but two ERC advanced grants, the latest in 2018, and received the biggest grant by the Willem Foundation, the Investigator Grant, in 2019. And just last year, he was basically also here, this was not even virtual, I think, and received the 2020 Herbert Walter Prize of the Optica Society and the Max Planck Institute for Quantum Optics. All right, so today we are looking forward, actually, Eugene, to hear the latest really of your work, for instance, on experiments with a macroscopic object, where now measurements exceeding the standard quantum limit can be performed. And so, Eugene, it's a great pleasure to have you here, and we are looking forward to your talk, and the floor is all yours.
Thank you very much. Can you hear me well?
Yes, we can hear you. Excellent.
Excellent. So it's a great pleasure to be invited to the Max Planck Institute and this general colloquium. There are many familiar faces. Thank you very much for the introduction. It's almost exceedingly good. So let me just get started. So the general theme will be quantum physics with macroscopic objects, and I will start gently. I'll talk about a macroscopic object of 10 to the 8 atoms. And what you see...
actually, Eugene, I just want to... So here's now the summary and outlook, and we are not in full screen now for some reason. I'm not sure if that's...
Okay, somehow I have it in full screen.
It worked before, interestingly enough.
That's because, when they asked me whether I agreed to share the screen, I said yes, and then something happened.
Maybe reshare and probably works then.
Yeah.
I also see the button resume slideshow. Maybe this is the key.
1 second.
Oh, yes, there's some resume slideshow button.
Boom, 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 boom. Hold on, so I'm screen sharing, stop share.
And I think if you just do slideshow, if you could just start the slideshow, it should work.
Okay.
Perfect.
So I'm starting. How is that?
Excellent. This works. Thank you, Eugene.
And like that also?
Yes, now we see one photon at a time.
Okay, good. Well, so one photon at a time from 10 to the 8 atoms. 10 to the 8 atoms is a lot of atoms, arguably a macroscopic object. And what you see in front of you is actually a piece of glass blowing art. But can you see my cursor also?
Yes, it's perfect.
So somewhere here, there is a small channel where a bunch of room temperature atoms is held. And this device, which is relatively simple and room temperature, can generate single photons, and I will tell you how it goes. And obviously, this is a competition to a great number of wonderful experiments on single photon generation, from ultra cold atoms, from cryogenically cooled solid state systems, and so on. And of course, MPQ is famous for experiments with ultra cold atoms in Emmanuel's group and Gerhard Rempe's group. So this is our humble attempt to compete with those people with room temperature atoms. So to talk about the ensemble spin memory and ensemble-based single photon, one cannot do it without gracefully referring to the original protocol of Donlukin, Sirac, and Solar. And this is essentially the first proposal for the ensemble-based quantum repeater, which is based again on the single photon. So what you see here is my drawing of first heralding that a quantum memory is charged with a single photon, and then retrieving this single photon by pressing a button. And this all is based on the collective interaction. So the collectiveness of the interaction is reflected here in the term which contains the number of atoms. And the beautiful idea of DLCZ was that if you don't know and you cannot tell which of the atoms has actually emitted a photon, then it will be quantum enhancement by the square root of the number of atoms. And therefore, one can work with atomic ensembles as opposed to single atoms in extremely high Q cavities. And this is based on the Raman transition. So the photon comes out because you first charge this memory and then you retrieve the photon in the inverse Raman process. So you can think of it as you first charge the memory and then you retrieve it. And there could be a delay between those two processes. So it's an ensemble, and it can be a large ensemble of many atoms, and light goes through. And in this first charging with the Raman process and then retrieving with the inverse Raman process, you can generate a photon. The thing is that atoms should not move, because you can think of this process as generating a spin wave. And it's like, loosely speaking, some kind of a diffraction grating, which is written in the atoms by the first process of the Raman transition. So when the triggering photon is emitted, then there is a signature of this photon left in the atoms as some sort of a spin wave. And if atoms further down move, then when you retrieve the photon, you will fail because this diffraction grating is essentially erased. So again, many beautiful experiments have been performed where those principles were demonstrated with ultra-cold atoms and solid-state cryogenic emitters. And what we want to try, and what we have actually succeeded in doing, is applying the same principle of collective quantum memory and ensemble-based single photon to room temperature atoms, which apparently move. So here is the situation that we are dealing with. We have atoms which are contained in this glass cell inside this little channel. Here you see a photograph of the whole cell. There is some cesium here. It's at room temperature, so cesium has some vapor pressure, and with some amazing glass blowing technique, cesium atoms are contained inside this little channel, and light goes through and generates a photon. Now, atoms move. All of them move. And light goes through and it interacts with those atoms, and at every instant, depending on which atom is where, this light essentially interacts with a different subset of atoms. So that's the challenge. And to overcome this challenge and to make this whole ensemble being a quantum memory for this one single photon, we need at least two tricks. So one of them is that when atoms move at 200 meters per second in this little cell, when they collide with the glass walls, they immediately lose all the spin coherence, and the spin state is essentially randomized. So what we do is we coat the inside of this cell with some special spin protecting coating so that the quantum state of the spin can be preserved for hundreds of thousands of collisions. So that makes atoms moving at 200 meters per second essentially a very good storage device for the quantum state of the spin. And even at room temperature, this memory time in this ensemble can be up to 10 milliseconds, depending on the size of the channels. For this small channel, that's like that. For larger channels, it can be approaching a second. Now, this is still not enough because, again, we need to achieve a superposition of all atoms emitting just one photon. And that means that atoms have to be indistinguishable in terms of emitting this photon, which means that we somehow need to erase the information of which atom can actually emit the photon. So this is a little more detailed picture of the same. And to erase this information about which atom contributed in what way, we need two tricks. The first trick is that the photon that is emitted is collinear with the light which excites this Raman transition. So this is the photon emitted, this is the light which excites the transition, and essentially what you see here is the phase which depends on the difference between those two K vectors, this one and that one. And you can imagine that if the photon is emitted at an angle, then this difference of the two K vectors will be of the order of optical K vector, which is submicron. And of course, it will not be possible to contain this quantum state because any motion of atoms will immediately ruin it. So we need to do the collinear protocol. On top of that, imagine that I have this photon emitted and there is a detector which produces a click. The moment this detector clicks is like a snapshot of the instantaneous position of those atoms. And if afterwards atoms move, then of course the next instantaneous position of the atoms becomes different and the spin wave again is erased. So we somehow need to make this motional averaging of the atoms. We need to observe the photon over the time, which is much longer than the transverse motion of those atoms. And this can be achieved by sending this photon through a cavity where the storage time of this photon will be longer than the characteristic time of the atomic motion. So this characteristic time at 200 meters per second with 0.5 millimeter channel, it's about a microsecond. So if we make a cavity where this photon bounces back and forth for longer than a microsecond, then we can erase the information about the configuration of the atoms that emitted this photon, and therefore we can have collective atomic state being written in the entire atomic ensemble. So with those two tricks, we essentially make this exponent to be 1 and make every configuration of atoms contributing to the spin wave in a similar fashion. And in this way, we achieve what we call a symmetric spin wave. So using those tricks, we put together the system, which is now a little more detailed and kind of closer to reality. So we use cesium atoms, we apply an exciting light, and we detect the first photon which heralds the charging of this memory. So this happens in this channel. And then we wait for the memory time that we want to explore, and we run the inverse process. And in the inverse process, we use polarization filtering, and we detect the photon which has been retrieved. So this is the conditioning of the memory being charged, and then we wait a little bit and retrieve a photon. So this is what we call the memory-based single photon source. And after the memory is charged, the source becomes essentially from the heralded, it becomes basically the on-demand photon. Of course, within the memory time. So we characterize this source by looking at the correlations between the heralded photon and the retrieved photon, and also by looking at the statistics of the retrieved photons. So what you see here is the probability that after the memory is charged and the light is retrieved, that we get 2 photons and not 1, normalized properly. So obviously for completely coherent state of light, this probability will be unity. For uncorrelated photons, now going below this level of the conditional G2 function, this is already non-classical. Now, if we go below 1/2 in this conditional probability, then we are actually, the state is dominated by the single photon contribution, but there is also some 2 photon contribution. And we are at the level of 0.2, so we are definitely dominated by the single photon contribution, and this is our best effort so far in generating a single photon from a room temperature collection of 10 to the 8 atoms. a little more about the timing and the memory of this system. We can look at the probability of generating the second photon conditioned on the charging of the memory. Apparently, the longer you wait, the more chances are that your spin wave has deteriorated for this or that reason. But still, if we look at the condition for the possible Bell inequality violation for two of those systems, then we can wait for 150 microseconds. And if we look just for the non-classicality of the retrieved state, then we can almost wait for a millisecond. So is it big or is it small? Well, half a millisecond is 100 kilometers of the propagation of the photon in a fiber. So it's a good beginning for the room temperature based single photon source. Obviously, a lot of work needs to be done. So let's consider this the introduction, and I will now change gears, and I will now talk about my quantum systems, not as, for instance, the sources of Fock states or the sources of single phonons maybe, but I will talk about it as oscillators. And this makes good sense because all the systems that I will tell you about, all the macroscopic systems that we play in the lab, can be considered under one umbrella of quantum oscillators. So, for example, I show you here a spin in magnetic field, and if my spin is optically pumped predominantly in the vertical direction, and I put it in the magnetic field along the same direction, then quantum projections of the spin will be oscillating around the magnetic field. And as I will show you in a minute, those two spin projections can be considered as renormalized quantum spin oscillator. Another relatively obvious story is the mechanical oscillator. Here things are simple. X and P are the position and the momentum of the oscillator. And if I look at the position of this oscillator in the lab frame, then the X operator will be responsible for the sine omega t and P for the cosine omega t. And finally, of course, at MPQ, people know that light is also a quantum oscillator, and the phase and the amplitude quadratures of this wave are also non-commuting variables like X and P. And the best of the news is that those X and P quadratures of light can be measured very, very efficiently through something which is called homodyne measurement on light. So let's introduce a few of those oscillators in more detail and then see what we can do with those. So here is a quantum mechanical oscillator, and it is described with the 0-point fluctuations in both X and P, and we can normalize the X with the 0-point fluctuations like that, and P with 0-point fluctuations like this. And for example, for the oscillators that we play with, the size of the 0-point fluctuation is about 1 femtometer. So the frequencies that we're dealing with is about a megahertz. And if you put the mass of about 10 nanograms, then you'll get to this 1 femtometer. And note that 10 nanograms arguably is a macroscopic system. You can see it. Well, I wouldn't advise you to touch it, but it's definitely something relatively macroscopic. So the 0-point fluctuations of an oscillator are achieved if it's cooled down to the ground state of its energy, essentially to the 0 Kelvin of a certain mode of this oscillatory mode. It still oscillates with those 0-point fluctuations. And the normalized X and P for this oscillation will obey the usual uncertainty relation with the commutator and so on. So what does this imply? That implies that X and P are non-commuting variables. So if you know one of them very well, meaning that this variance is small, you pay by imposing a lot of disturbance into the other one. So you're not allowed in principle to measure both X and P simultaneously. And this process of imposing fluctuations on P by measuring the X, this will be dubbed as quantum backaction of the measurement. So let's look at this quantum backaction mechanism in a little detail. So imagine that I'm measuring the position of my oscillating membrane, and it's given by X times sine plus P times cosine. So let me look at it in some kind of a phasor diagram where the rotation will be like motion in this direction. So imagine that in the first instance, I'm making a measurement, and I make the measurement at time equals to 0. That means, that I'm actually, I'm making a measurement when the cosine is 0. So I'm making a measurement of X, and at the same time, I give a quantum backaction into P. So that means that I measured X, I put the backaction into P, but the oscillator is oscillating, so there is a rotation in this rotating frame, which means that after another quarter of a period when I measured P, I put the backaction into X. And with the continuous measurement, the more I measure, the more backaction I put in. So essentially, there is probably a good measure of the strength of the measurement, which balances the initial uncertainty and the backaction. And this good measure produces the so-called standard quantum limit. The point that I will try to make in the next 15 or 20 minutes is that, in fact, if I choose the correct reference frame for this measurement, I can beat this limit on the measurement of motion. So the statement is that arbitrary small perturbations in both position and momentum can be measured simultaneously, just if we find the right reference frame for it. So before going any further, let me just give you another snapshot on this origin of the standard quantum limit. It's kind of a textbook story. And being from the Niels Bohr Institute, where, you know, they say that Heisenberg microscope is what I'm going to tell you about, was conceived by Heisenberg when he was meeting Bohr. I don't know about that, but here is the story. So we have a particle and we want to observe it. Observing the particle means scattering a photon from it. So we scatter a photon, this photon is observed, and the particle gets a kick. But that's not the whole story. The whole story is that the photon is also a wave. And if we focus this wave very tightly on the particle, that essentially means that the scattered photon will be a diverging wave. This diverging wave will have the uncertainty of the momentum, and this uncertainty of the momentum will be reflected on the particle. And so this is basically the origin of the uncertainty relation between the how well we measured the position where the particle was and what is the uncertainty of the momentum that we impose on it. And if you put a little arithmetics in it, you will actually see that the position of the particle will be the initial position plus the momentum times t over m. And given that we have the uncertainty relation, you can rewrite the variance of this position using the uncertainty relation, and you will arrive at the Stern quantum limit. And my goal here is to show you that this is all true in the classical reference frame. If you choose a suitable quantum reference frame, then you can beat this limit. So we called it initially trajectories without quantum uncertainties. In the negative mass reference frame, there is also another way to refer to it due to Karl Kave's, which is quantum mechanics free subspaces. Anyway, it's the same story. So you have a classical trajectory of a particle, and you have a quantum trajectory, which is uncertain. And the point is to make the quantum trajectory as well defined as the classical trajectory. So 3 steps that you need to make on the way there. Number 1, you have to define the trajectory of an object relative not to just a typical classical reference frame, but a quantum reference frame. You have to choose this reference frame with an effective negative mass, and I'll tell you in a minute what it means. And finally, you need to generate an entangled state of this reference frame and the probe system. And if you go along those 3 conditions, then you can observe whatever disturbance is imposed by external forces on your system, then you can observe it with, in principle, no limitations. So I'm sure all of you know about the APR entanglement, but let me just refresh your memories real quick, because this will be an essential part of the story. So back in 1935, Einstein, Podolsky, and Rosen came up with this argument that there could be 2 particles with x1, p1, x2, p2. And because the difference of the positions and the sum of momenta, they commute, obviously, because of this minus sign, then you're allowed to measure them simultaneously with arbitrary accuracy, the total momentum and the difference of the positions. And if you're allowed to do that, then you can do tricks. And in fact, Einstein, Podolsky, and Rosen were very unhappy with this because they thought that something is wrong with quantum mechanics. Well, so far we're happy with quantum mechanics, and it is nice to actually realize that 65 years after this qualitative criterion was formulated, Duan, Giotke, Sirac, and Zoller, they actually formulated a quantitative criterion for the entanglement. We don't need to know the sum of the position, the sum of the momenta and the difference of the positions with infinite accuracy. We just need to know them a little, well, somewhat better than a certain level. And where does this 2 come from? This 2 actually comes from a relatively straightforward considerations, because if you have the regular uncertainty relation for x and p, then the minimal uncertainty for a vacuum state, for example, or for a coherent state, will be 1/2. And if the 2 systems are not entangled, then you can break this variance into the sum of 2 variances, and this one into the sum of 2 variances, and it will be 1/2, 1/2, another 1/2, another 1/2, which is 2, and if it's less than 2, then it must be entangled. So let's see how far we can get if we take 2 particles, and one of them we take as a reference particle. And this will be the particle with a knot. So X naught, P naught are the operators pertaining to the reference particle. And we know that we can achieve the state where the difference between the X's and the sum of P's is absolutely well defined. So let's look at the trajectory of our particle as a function of time with respect to the reference particle X naught. It will be the difference between the initial positions plus the difference between the derivatives times time. This is obvious. And if the difference between the derivatives can be written as the difference between the momenta, I take mass to be unity. And what? Well, doesn't help, because this is the difference of the positions and the difference of the momenta. They don't commute and the trajectory still diverges. But now already here, you see what I'm aiming at. If I manage to change the sign here by somehow coming up with a system which has an effective negative mass, then the trajectory of my particle in this reference frame with a negative mass will be given by two commuting variables, the difference of positions and the sum of momenta. And then I can measure it once, and then I know it, and therefore, if I have any perturbation on either X or P, I will be able to observe it within principle of limited accuracy. And the same can be discussed with the oscillator, because again, for the oscillator, it will be the rotating frame variables X and P, and you can write down the difference between the observed positions of the two oscillators. And now I'm relying on the fact that the effective frequency of my reference oscillator is negative. And the system that I will introduce in a minute will actually have the effective mass negative, effective frequency negative, and even the effective elasticity negative. So it's a stable oscillator, it's just inverted. So before we go into details of this story, let me show you the mechanical oscillator that we are dealing with. And I would like to highlight my student Yegish Etzeterian and my colleague Albert Schließer, who contributed to the development of those wonderful oscillators. And it's a dielectric membrane. The size of it is 3 by 3 millimeters, and it has a very elaborate phononic band gap structure. This structure is designed in such a way that the central oscillator is extremely well isolated from the environment, from the frame, and therefore it can have an astronomical Q of about 10 to the 9 or a little better. Excuse me. So if we are able to cool this oscillator to the 0 Kelvin motional temperature, we will be only limited by the ground state noise of this oscillator, which is about femtometer, as I told you before. And this is our operating conditions. Some of you probably know about the basics of quantum optomechanics, but let me give you a real quick walk through it. So how do we interact with light with an oscillating object? So let's take this oscillating object, the membrane, put it between the two mirrors and send light in. There is a standing wave, so this dielectric object oscillates, and if we don't put it in the node or antinode, but put it somewhere in the middle, then the dielectric object oscillating in the standing wave will modulate it. And it will modulate it at the frequency, the light will be modulated at plus minus mechanical frequency. So let me first assume that I tune my laser on the blue side of the cavity resonance. So that's the cavity resonance. Oscillating membrane will create the red sideband at minus mechanical frequency and the blue sideband at plus mechanical frequency. Clearly, if this is the cavity resonance, the red sideband will be generated much more efficiently. And that means that we are scattering a photon from the higher energy to the lower energy. And this energy that we have lost in this scattering process should appear somewhere, and it appears as a quanta of the motion. So by scattering from the carrier into the red sideband, we are creating a phonon and creating a photon. And this is an entanglement interaction. If now I tune my laser on the other side of the resonance, then I am generating a blue sideband, a blue phonon. That means that I have to take out the energy from this mechanical resonator. And that means that I am generating, I'm making sort of a beam splitter interaction where light, which actually at a megahertz frequency has 0 noise temperature. Those of you who work with quantum fluctuations of light know that at 1 megahertz sideband frequency, light is typically shot noise limited. That means that there are no excitations. That means that light at 1 megahertz sideband is basically a refrigerator. So if I put it in contact with my mechanical object, which is pretty hot, I will just be taking away the energy, which means I will be cooling it. So I can optically cool my mechanical system, and then I can make measurements on it, because, for instance, if I put my laser smack on resonance, then both those terms will contribute in the same way, and I will get something which is called a quantum non-demolition interaction, where measuring one of the quadratures of light, I can get information about the quadrature of the mechanical motion. So that's kind of a crash course on quantum optomechanics. And now here is the performance of our system. We take our membrane, we place it in the optical resonator, and we shine light on it. So because of this wonderful phononic bandgap structure, on the resonance frequency of our oscillator, which is around 1.4 megahertz, we see a beautiful peak. And this beautiful peak actually is purely quantum. If I zoom into this peak, this is what I see. And this is with only shot noise limited light thrown on this system. And what we observe is pretty much mostly the back action of light on this mechanical object. So shot noise fluctuations of light, of the amplitude of light, are shaking this membrane, and its noise is dominated by this shaking. In fact, the noise of the membrane itself, which is cooled almost to the ground state by this optomechanical cooling, as I mentioned, is essentially extremely small. So we're in a good position here. We are making a measurement which is dominated by the quantum back action. And if we manage to cancel this quantum back action, then we should be able to make a measurement with, in principle, unlimited sensitivity, because the shot noise measurement is really small. So now we have our mechanical oscillator in a good state. That's the part of the experimental setup where we place this membrane in an optical resonator inside this modest cryogenic device. It's not a dill fridge. It's essentially 8 Kelvin. And now let's go to the atoms. So as I told you in the beginning, we need a negative mass oscillator. So imagine that I have an atomic system and for simplicity, a spin 1/2 system, and I optically pump all my atoms in the spin up state. So in the Bloch sphere, I have this macroscopic spin, and if the atoms are uncorrelated, there will be the minimal uncertainty noise, the coherent state of the spins. Imagine now that I make any excitation on the atomic state. This is the minimal fluctuations that are allowed. So any other state will have larger fluctuations. For example, if I make a single excitation, as we discussed in the beginning of the talk, it will have the distribution which looks like that. So it's kind of a Wigner function of the first excited state. The size of this is bigger than the initial coherent state, vacuum state. And if it's bigger, then because of the curvature of this Bloch sphere, it will be closer to the ground state. And if it's closer, it's closer to the South Pole. And if it's closer to the South Pole, that means that it has low energy. So we have created an excited state of an oscillator which has the energy which is lower than the ground state. And it's pretty obvious from this picture also. So this is a relatively simple incarnation of the oscillator with the negative effective mass or negative effective frequency. And you make it oscillating by placing it in the magnetic field. So now we have a mechanical oscillator, our regular positive mass object, and we have a spin oscillator, which is the negative mass object. This is just an illustration of what we have already seen, our atomic ensemble at room temperature. It's very similar to what I've shown you in the first part of the talk. Again, we put it in the magnetic field. Atoms move around, but they keep their coherence for a very long time. And now let's look at the measurement with atoms. So to make a measurement of the spin, we just make use of the Faraday effect. You send linearly polarized light, and because the projection of the spin on the direction of propagation of light oscillates, the polarization of light will also oscillate. And this oscillation of polarization will read out the projection of the spin on the direction of propagation, as simple as that. So you make measurements on this spin oscillator, but while you measure, it of course oscillates, it rotates. So as I told you 10 minutes ago, you make a measurement of this projection and you impose the back action in this projection, and then quarter period later, they swap. So the longer you measure, the more back action you get. And essentially you're dominated in your measurement, again, with the back action of noise. And this is what we have for the atomic spins. So now we have two systems, the mechanical system dominated by the quantum back action and the spin system dominated by the quantum back action. And now we put them together. So we put them together, we publish a paper, and it's the atomic system in the effective negative mass state. And that's what's happening. So we have our atomic system here, we have the mechanical oscillator in a cavity, and we send light through. The two systems that you have seen before. And the point is that when we send light through, we have the short noise of light, and we have the back action imposed on light by light on one system and the back action imposed by light on the other system. And if we don't have any losses, then those two operators are the same operator because it's the same light that goes through. And now, if we manage to have the spin system with the same response function, chi, and the same coupling constant, gamma, as the mechanical system, but with an opposite sign of this, then we can have cancellation of the back action, as we discussed qualitatively before. And the result is shown here. Indeed, we make a measurement of the quantum noise on the mechanics alone, and it is dominated by the quantum back action, this dashed area. We make measurements on the atoms alone, and there is a significant portion of the back action here. And then we just change the magnetic field and we move the atomic resonance frequency to overlap with the mechanics resonance frequency, simply by changing the magnetic field. And what we get is a significant noise reduction of this area with respect to this one. Note this is the logarithmic scale. So here we have close to 10 to the 2, and here we have significantly smaller. So the bottom line is that the noise reduction, that the quantum back action is canceled by a factor of 4, by 4 dB. And this again happens because we're dominated by the quantum back action in both systems. One of them has an effective negative susceptibility, and when we put them together, we cancel the back action. So those are heroes from the lab. And using this principle, very recently we have demonstrated that we can actually generate an entangled state between those two systems. Basically, the difference between demonstrating quantum back action, cancellation, and the entanglement is simply in the quality of the experiment. So in the 2017 experiment, we didn't have low enough noise of the spin system and significant low enough losses between the two systems, and we couldn't demonstrate entanglement. Then we improved the system and we got there. So before I show you the results, I just want to pictorially demonstrate this kind of entanglement so that you have a sense of it. So here are the two systems again in the XP frames, and the mechanical system is cooled close to the ground state, but of course this only happens on a certain time scale. So in fact, if we wait long enough, then it will jump inside this initial thermal distribution. But if we make measurements faster than those jumps occur, and this is possible here, then we can forget about the thermal quanta. And then we can zoom into the instantaneous quantum state of the mechanics. The atomic system, as I mentioned, can be near the ground state simply because of the spin temperature. And now, how do we visualize this entangled state? We make a measurement and we get random outcomes within the quantum back action uncertainties. But those two random back actions are always correlated because the two systems are entangled. So they can be like this, they can be like that, they can be like this, but they're always correlated, which means that if I make those measurements and then I come a millisecond later and make a measurement again, and I see that they're not correlated, then one of them has been exposed to the perturbation, which I can measure, and I can measure it in both X and P projections simultaneously, because I'm allowed to measure P1 plus P2 and X1 minus XP2. So the quantitative results are here. We generated entanglement. It's a modest entanglement, but never mind. We started from the variance which was significantly higher than the entanglement threshold. And by making those measurements and verifying the entanglement, we achieved something like 1 decibel below the threshold of the entangled state. Let me skip this. Okay, so in the last 5 minutes, let me tell you about yet bigger objects that we're aiming at. And those are arguably the largest mechanical oscillators in the quantum regime that people are dealing with. And those are the gravitational wave interferometer mirrors. So we've all heard about the gravitational waves, and they were detected, and this has become a very active research field. So just to remind you how those waves are measured. So they make an interferometer, this kind of interferometer, and those two mirrors are suspended like that. The gravitational wave is a quadrupole wave, and it moves this mirror and this mirror out of phase. So it unbalances the interferometer, and this unbalance is measured by the detector here. And they can measure those positions of the mirrors with an amazing accuracy. The accuracy is of the order of 10 to minus 23. So the relative change in this position with respect to this length is 10 to minus 23. But the best news for us is that they are actually limited by the quantum fluctuations of those mirrors. So at higher frequencies, they are limited by the shot noise of this light. And at lower frequencies, they are limited by the back action of light, which it imposes on those mirrors. And as I just told you in great detail, we are possessing the method which can provide the broadband cancellation of both shot noise and back action noise in the system. This you have seen before. It's again the quick reminder about the fact that if we don't impose quantum fluctuations, then the uncertainty of the position and the momentum are balanced, and they lead you to the standard quantum limit. And this is what I've shown you in the previous drawing. And the mirrors of those gravitational wave antennas are suspended in such a way that they are pretty much almost like a free mass. So the discussion for the free mass is quite applicable. So what we propose is to take our little system, the atomic noise eater with the negative mass, and place it in one arm of this interferometer. Well, it's not exactly just this cell with atoms, but given that this system is 4 kilometers in size, our system is really small. It's a 2 meters by 1 meter breadboard. And the point is simply that if we manage to generate the atomic response due to this negative mass and negative susceptibility, which matches the response of the mirror oscillator, but has an opposite sign, as this atomic system has the effective negative mass. Then we can cancel those two perturbations and make a measurement which is free of back action. Something like that. You make a measurement, joint measurement on the two systems, the interferometer and the effective negative mass, and you take the difference between the two position operators, the difference between the two momenta, and because the mass is effectively negative, you can cancel both difference of x's and sum of p's and have in principle unlimited accuracy. There is a number of technical problems. One of them is that we cannot use the same light source to interact with both systems as we did in the lab, because atoms want to interact with resonant light, and the LIGO people want to interact with the 106 laser, because this is where they spent God knows how many $1 million to build. So we have to come up with the entangled light beams. And that would be the substitute. This parallel scheme with two entangled beams would be a substitute for a sequential scheme with one beam only. So without making it too long, this is still, in the lab. We're still working on it. We made some simulations where we hope to encourage the gravitational wave community to attract their attention to our principles. We're building the system, and this is our tabletop setup. And we hope to demonstrate the proof of principle without any gravitational wave interferometry involved somewhat soon. And this is my summary and outlook. So I hope I've convinced you that macroscopicity of systems is not a big obstacle in terms of generating interesting quantum states, including entangled states. And this will have, hopefully, interesting implications in measurements and quantum communication. And another thing that we're hoping for is to start generating distant superpositions of macroscopic objects and maybe approach some interesting regimes for exploring the boundaries of quantum mechanics. Thank you very much for your attention.
Thank you very much, Eugene, for this really beautiful talk, and actually very also pedagogical, so we could learn a lot. Thank you. So we have time for questions. So I would suggest you just unmute yourself or type in the chat if you want to ask something. Maybe let me start with the first one. That's concerning the first part of your talk, Eugene. These vapor cells which you have, is it that they are, my question is, are those per vapor cells saturatable emitters? How many, I guess you're working on the Rydberg transition?
No.
No?
No, this is a standard. So note that all the superpositions,
it's just 6p.
Yeah, all the superpositions that we're generating are in the manifold of the ground state. So
Okay.
those are just two magnetic sublevels of the ground state of cesium. And the transition that we choose Well, there are subtleties, but in principle, it can be pretty much any transition. So we choose, the D2 line, D1 line of cesium because it has high dipole moment and it's easy to couple to.
So when you say that you generate this dark state polariton type of wave function,
yeah,
that assumes a single excitation. I should view this in the low power regime of the laser?
Yes.
Okay.
No. You should view it as the single excitation in this magnetic manifold of the ground state. So you have all the atoms in the initial magnetic sublevel. You create a collective excitation corresponding to the neighboring magnetic sublevel, and it's the superposition of this single excitation over all the atoms. So it's kind of a quantum coherence on this manifold, which is storing the single excitation.
But how did you ensure that you just have a single excitation?
So you make this process so low probability
Okay.
that there is either nothing or one.
Okay. Yeah. Thanks. Great. Maybe let me ask me one more to the second part of the talk. So as I understood, you have one quantum system which has to serve as the reference, where basically you measure the distance of two quantum objects by the quantum observable of one. And then the thing was that this one reference thing should have a negative mass.
Mm-hmm. Is
there anything of interest in looking into observables where you have multiple X1s? So multiple systems where you want to measure the distance from your reference.
It's a good question.
You could imagine like a molecular state. There you could ask, I have one part of the molecule, which could be the reference position, and you want to measure maybe the second part of the molecule. Let's say we would have N2, but maybe you want to measure something like about CH2, and then you would have two H atoms and one C. Is there anything what you could learn by extending what you have shown?
So it's a very good question. And in fact, since whatever, 2009 or something, when this idea was kind of formulated and spread really wide, people have come with several proposals on how to use it. And indeed, you can find similar systems. I think Pierre Maistre has done some work with his collaborators. It wasn't like you say two atoms in a molecule, but it was a ultra cold atom system, and they found the analogs of the negative mass in the ultra cold atom systems. So yes, indeed, if you find suitable systems with either this kind of inverted population or some analog of the negative frequency state, then you can make measurements which will be principle with unlimited accuracy. Yeah. There were also ideas, as far as I recall, about electrons and positrons on the boundary in the solid state, because you can think of positrons as the systems with the effective negative mass.
Yeah, we could think about creating excitons at an inverted band, where the electrons possess a negative band curvature.
Yeah, so the big trick essentially here is to find the two systems which have a reasonably high Q factor, because all this business is based on the fact that you can somehow achieve the ground state and then maintain the entanglement for a reasonable time.
Then maybe the electrons are not the best.
Well, we also, with Jung Yi, we came up with the extension of this idea to the clock. So he proposed an interesting atomic state system where through the four-wave mixing, you could generate an analog of the negative mass reference frame. And he thought it was cool, but it was already 5 years ago. I still don't see any clock like that, but they're busy people.
Thank you. Okay. Let's see, Gerhard.
Eugene, first of all, hello.
Hi.
And thanks very much for this very nice talk. I was wondering, you mentioned that the single photon emission efficiency is kind of small in the DLZ scheme. Can you imagine that the mechanical oscillators, the membranes, at some point or in some way provide a better source for single photons?
Well, thank you for a question, because actually I was thinking of throwing in another subject in this talk, but I was wise enough not to do it because we are actually working on the generation of the single phonon excitation in the mechanical systems, just like you said, by cooling the mechanical system to the ground state and then generating a single excitation by scattering a blue detuned photon. So that's one story. Another story is that, in fact, maybe I wasn't clear enough, but those principles, they are like we discussed with Richard a minute ago, the generation of excitation has to be a low probability process because we don't want to generate two. But as soon as we have generated this excitation, then because of this collective enhancement, the retrieval of the second photon is actually not probabilistic. And according to our calculations, the intrinsic retrieval of this stored spin wave is close to 100%. We don't know exactly, but it's definitely above 70%. So the fact that what we get on this detector is, something like maybe 10 to minus 2 probability is purely technical limitation. This is essentially only losses. So the first process has to be probabilistic, but the retrieval can be rather deterministic.
Eugene, I know this. That's clear. Yeah.
Sorry. But maybe you can repeat your question.
Well, the question is, in the end, I mean, if you can make a phonon deterministic with a membrane, can you convert this phonon then into a photon?
Absolutely. And this is the experiment that I just referred to. And there is a paper which we published. It's not yet the single phonon generation, but there is an Optica paper where we kind of do the precursor for that. And basically,
and would that be deterministic, Eugene? Or kind or quasi-deterministic?
Well, it will be the same principle that we cool it to the ground state, then we generate the excitation by low probability scattering of a photon, and then we can retrieve this excitation after the memory time of the membrane back into the photon. We can also, and this is what we plan to do, we can look at the Wigner function of this macroscopic object and hope to see negativity. So
okay, yeah. Can I ask another question, Eugene? It's a little bit unrelated, but if I understood correctly, when you introduced this black holes, the LIGO collaboration and so on, you mentioned, if I understood correctly, you mentioned that the merging of two black holes is something quantum?
No.
Okay. Maybe I misunderstood you. Okay.
No, for me, all this astrophysics is just the source of gravitational waves.
Yeah.
And I'm talking to astrophysicists and trying to learn a little bit about those objects and about the spectra. And I learned that, in fact, they find more and more interesting astrophysical events in all ranges of frequencies, from millihertz to hundreds of kilohertz, and that makes us rather happy because our system will work better in one range of frequencies than in the other. But this is as far as my astrophysics knowledge is concerned. Quantumness here are only limited to the measurement of motion of the mirrors of the gravitational wave interferometer beyond their ground state.
Yeah. Thank you.
Thank you.
Do we have more questions? That's my chance to ask one more.
Sure.
Eugene, you mentioned that your experiment, as one sees in the pictures, like 2 meters. Now you had the reference, which was your atomic system with a negative mass, and you had your resonator, no, your basic mirror.
Yeah.
Could the reference system be inside the mirror? In the sense, is there a need for spatial separation? Let's suppose I take a 2-dimensional semiconductor, which is a perfect membrane. I could make it free float, not free floating, of course, but suspended. And if the excitations, the atomic system, the equivalence of the atomic system would be inside the mirror, would that be, is there a problem with that? Did you need spatial separation that the laser was propagating through? First the one and then the second, was there importance about the delay there or not?
That's, again, very good question. And the answer is no. The spatial separation is not a requirement. But yes, I thought that this will be a very interesting twist, because to me, first of all, if you make those two objects entangled at a distance, then you can also use them, for example, for a repeater. You can also use them for teleportation. You can use them for spatially separated measurements of forces and acceleration. So our drive was actually to try to make them distant. We thought that this would be cool. If it's of interest to put them in one resonator, in fact, there is a recent experiment from Treutleins group with Clemens Hammerer as a leading theorist, where they actually put the atomic system and the mechanical system in one extended resonator and also found some rather exciting results. So what you are proposing is even closer merger. That is, it's, you know, I've been wondering about it too. I was thinking, can we like take a diamond vacancy and then, you know, put it on top of this membrane and see what happens there. On paper, yes. Experiment, I don't know how to do it. If we were able, like I think Peter Zoller and collaborators had a proposal at some point where they considered a mechanical object and a 2-level system embedded. And then because of the deformation of the mechanical object, the 2-level system energies were perturbed. And then, of course, sky is the limit if you can reach such a system.
Yeah. Thank you. Okay. All right. Do we have more questions? If that's not the case, let me thank Eugene again, also in the name of MCQST, so our center here on quantum science technology, and also thank you that you take your time also for the meetings this afternoon with with the members here of our excellence cluster.
Thank you very much for the
It was really nice to have you here.
It was a pleasure, and it was great seeing some of you.
All right, and I see you later as well. So actually for the meetings, I think, Barbara, we can stop the recording.